This is Advent of Code, day 24 in OCaml in 3, 2, 1, go. Day 4, Blizzard Basin. With everything replanted for the year, you and the elves leave for the extraction point. Partway up the mountain that shields the grove is a flat open area that serves as an extraction point. Bit of a climb, expedition can handle it. That would normally be true. Things that are difficult because it's covered in snow. It reaches a valley that must be traversed to reach the extraction site. You find that strong turbulent winds are pushing small blizzards of snow and sharp ice around the valley. It's a good thing everyone packed warm clothes to make it across safely. You'll need to find a way to avoid them. Fortunately, it's easy to see all of this from the entrance to the valley, so you make a map of the valley to the blizzards, your puzzle input. For example, the walls of the valley are drawn as pound signs. Everything else is ground. Clear ground where there is currently no blizzard is a dot. Blizzards are drawn with an arrow indicating their direction of motion, up, down, left, or right. The above map includes 2 blizzards, one moving right and one moving down. In 1 minute, each blizzard moves one position in the direction it is pointing. Due to the conservation of blizzard energy, as a blizzard reaches the wall of the valley, a new blizzard forms on the opposite side of the valley, moving in the same direction. After another minute, the bottom moving blizzard has been replaced by the top. The new downward moving blizzard at the top of the valley instead. Because they are made of tiny snowflakes, they pass right through each other. They occupy the same position marked 2. Great. After yet another minute, the rightward facing blizzard is the right is replaced with the new one on the left facing the same direction. Holy cow, here's a more complex example. Your expedition begins in the only non-wall position in the top row and needs to reach the only non-wall position in the bottom row. On each minute, you can move up, down, left, or right, or you can wait in place. You and the blizzards act simultaneously, and you cannot share a position with the blizzard. During the above example, the fastest way to reach your goal requires 18 steps. Drawing the position of the expedition as E, one way to achieve this is, okay, minute 1. We move down. Holy cow. There are 3 there? Oh, 3 here. Got it. Minute 2, move down. Minute 3, wait. Minute 4, move up. Fewest number of minutes required to avoid the blizzards and reach the goal. Holy cow. Okay, there are no blizzards going up or down in this column or in this column. So I can assume that it's not. Okay. Wow, that is that's a lot of spaces. Okay. I think a key insight here will be we don't need to compute, we don't need to move all of the blizzards at once. We can just check whether a blizzard will hit that position. So blizzard E so we have oops. By x equals module blizzard. This is really a valley. Type t equals of horizontal of int vertical of int. Can I name these? Type blizzard def equals offset int equals horizontal equals row int offset int delta int vertical call horizontal vertical. By x is a int comma blizzard dot t list hash table t by y oh H blizzard oh no blizzard okay there we go. Okay. Cool. So parse input. Let x equals hash table dot t equals hash table dot create module int in y let add blizzard add blizzard buys I'll just call it by z blizzard equals hash table dot change by z function none blizzard some blizzard some blizzards some blizzard blizzards in val take drop let lines equals in let height equals list dot length lines minus 1 no minus 2 in let width equals list dot length list dot head x and lines minus 2 in width int height int okay list dot iter I let lines equals list dot drop lines 1 list dot take height minus 1 in lines y line let cars equals list dot take string list dot drop string dot list line 1 with minus 1 in list dot iter car iter I cars fun x ch do match ch with let create offset delta equals offset delta. Add blizzard by y blizzard dot create offset x delta 1. With height by x by y. Oh. No. Blizzard.t a some blizzards. There we go. And what is wrong with this? String that length. Okay. Let valley equals valley dot parse input. Okay. And then let space let open at t time equals point. Let horizontals equals hash table dot find xn. Or I guess this isn't. Find or add. Yeah. Find or add t dot by x point dot x. dot x y equals point in x in list dot for all horizontals fun b wizard dot open at time y t dot width and verticals height. Time. Size by y width size height size height. Oops. Let size int. Let open at time t time pause time equals pause -3 mod 5 0 mod 5 1 mod 5 -1 mod 5 -2 mod 5 -3 plus 5 mod 5. Perfect. Offset plus delta times time mod size not equal pause. For x equals valley dot equals 0 to valley x minus 1 do print open at time t equals if valley.open at time valley point.create xy time then printf no blizzard at time x y time. Print open at time 0 1 2 All right, so 0 1 is open, 0 3 print s sexp valley.by x blizzard.t list. All right, so it's first by x. So there's a 1. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Print end line, print end line, string dot cars. 1, 2, 3. Of car list. Lines. Oh, that makes sense. So we have 2, 0, 0, 1, 2, 1, 3, 1, 2, 2. And now we have 0, 0, 3, 0, 5, 0, 1, 1, 2, 1, 5, 1, 2, 2, 5, 2, 2, 3, 3, 3. Perfect. If x equals 0 and y equals -1, or x equals t dot width -1 and y equals t dot height minus +1. T dot height. Then true, else. Yeah, is this right? This is 0, 1. So this is 0, -1. And then this is 3, 3. So this is 4, 3. So this is 5, 3. So 5 is 2, 3 with -1. And then this is 5, 4, which is the height. Okay, perfect. Okay. Let Q module state equals struct type t equals pause point dot t time int let create point pause time. Let states equals hash set dot create module state. let start equals let in bounds point equals let is start. Whoop. Is end. If is start PT or is end and true. Else x 0 is less than equal x and x is less than t dot with and 0 is less than equal y and y is less than t dot height. Okay. Equals point dot create 0 -1 let end equal end equals point dot create valley in q let q equals q equals q dot of list state dot create start 0 in let got to end equals false equals ref false in while not got to end do let deltas neighbors and same t equals let neighbors and same deltas equals 0 0, 0, 1, -1, 0, 0, -1, 0, 0. Equals list.map neighbors and deltas fun dx dy create t.x plus dx dy plus dy point dot neighbors list dot iter fun next let state equals q dot dq x in q in let state dot pause time equals state state dot pause time pause next pause if not got to end and valley dot open at time valley next pause time plus 1 then if point dot compare next pause if point dot compare pause end equals 0 then print part 1 time got to end true else open at time map then let next state equals state dot create next pause time plus 1 in if hash set dot if not hash set dot mem states next state then hash set dot add states next state q dot in q in bounds if valley dot in bounds valley next pause Mm-hmm. 18. $290. Let's go. Let's go. He forgot his snacks. Oh my God. Okay. Let time to point starting at equals start at dest. Ref none. Some time. Option dot is none. Arrival time. In. Option dot value accent arrival time. Print part 1. Let time to end equals time to end 0 in print part 1 time to end let time back to start equals time to start time to end in back to end equals time to back to start. To end. $30. Ooh. Oh. Start time. Time to start 805. Oh, shit. Huh? $17. There we go. 54. 41. Come on. Oh, okay. 842. Let's go. All right. This one. Oh, I'm almost there. Okay, so for this one, we have this blizzard going on where we basically have a bunch of, we're in this grid and there are these things moving along this grid, either up, down, left, or right. And everything moves at the same time. And we start at this point up here and want to move places when we can. And eventually we want to get down here. Rather than like keeping track of everything at each time point, because when these things, they like move to the right and then they loop around. So you can know where everything will be at any time in the future. You don't need to like compute every incremental state. So I have a point class, and then I have a blizzard, which is like it's offset. So for this one, it's 0. For this one, it's 4 or 3, the starting offset. The delta, basically how much it'll change each round, which is either 1 or -1. And then the size, which is how big of an area it's traversing, which it looks like might always be square. And then we can just check if it's open at a time, or I guess like at pause at time. Open at time. Not at pause at time. Oop. Yeah, so we can just check whether the blizzard is at a position at the time. So then we need to parse this. So and then we can keep track of all of the blizzards along a certain row or column, which makes it still a little bit faster. We only need to check, like when you're at a point, to check whether that point is free at a certain time, we only need to check the blizzards in that row or in that column. So I have the width and height of the valley, and then all the blizzards by by x by row by, oh, nope, that was a mistake, by x by col by y so we have all the valleys, all the blizzards by row and column. Yeah. And so we create the hash tables. We have this function to add a blizzard at a certain point. Then we loop over all the lines. We chop off like the first and last columns. And then if it's like a greater than sign, we add a blizzard at that. This is a row. And this is a col. Add a blizzard at that row, and the blizzard, it's offset by the current column. It's going to the right, so its delta is 1, and it has size as the width. And so we do that, and we have all of our blizzards. Then we have some helper functions to check whether we're at the start or at the end, which are kind of these special positions. And then to check if it's open at a time, if it's the start or the end, it's always open. Then we get all the horizontal blizzards at that point, at that column and row, and we check if all of the blizzards at that point, they're not at that point at that time. And then we know if all of them are not at that point, then it's open. Then we also have a bounds check function. So then we have this function time2, and this should really have keyword arguments. I will add that dest. So we just pure depth first search. We have a queue of all the states that we've been in, and the state is just the position combined with the time. And we first are at the starting point at the starting time, and we have no arrival time. And then while we don't have an arrival time, we get the next queue, get the next state from the queue. If we are at the end, then we set arrival time to be some time. Otherwise, we loop over all the neighbors and the same point, which is also including the 0, 0 delta, and all those next positions. And if it's inbounds and the valley is open at that time, then we could try moving there. And so we create the new state, and then I just thought maybe we would have duplicate states, so I only add it if we haven't seen that state before, to reduce combinatorial explosion. And then we enqueue the next state. And so then once we see one that's at the end, we set the arrival time, and then it breaks, and then we just return that arrival time. So part 1 is just the time to get to the end, and then part 2 then we're at the end and we need to go back to the start. So then the start is the end and the end is the start. And then, so part 2, we go to the end, go back to the start, and then go back to the end. So time back to the end is time to the start to the end, starting at time back to start, and that's the time back to the end, and that's part 2. So that is it. That is December 24th, 2022 solution. Cool.